So there are two pillars in physics, as per my understanding. There's on one side we have theory of general relativity, and on the other side we have quantum mechanics. And from what I understand, physicists are basically trying to combine these two pillars to make a general theory to understand the universe. Uh, but what's the problem with that integration? Can you explain that to me?
Yes, so general theory of relativity is Einstein's theory of gravity, which generalizes Newton's law of gravity. So if you remember your high school physics, Newton's law of gravity says that let's say the force between the sun and the earth is proportional to the mass of the sun, mass of the earth divided by the square of the distance. That's Newton's law of gravity. Einstein's general theory of relativity introduces time in this picture. Newton had this action at a distance when he talked about gravity. According to this law, you would just put zero as the mass of the sun if the sun disappeared. It would look like that the force of gravity will instantaneously disappear. And that's clearly absurd. And actually, Newton understood that this is absurd. But we know that light takes 8 minutes to come from the sun to earth. So how can it be that force of gravity travels like almost like in an occult fashion, instantaneously at a distance? And this remained a puzzle actually for 200 years. And the final resolution comes in Einstein's general theory of relativity. And because force of gravity, like any electromagnetic, just like electromagnetic influence goes at the speed of light, gravitational influence travels at the speed of light. And that's what is the source of gravitational wave. So Einstein's general theory of relativity incorporates the speed of light as the upper limit. As a result, it has two consequences. One is general theory of relativity predicts that there should be gravitational waves, which were detected a few years ago, which got the Nobel Prize, the LIGO experiment, and it predicts black holes, which also got another Nobel Prize, somewhat indirect. That's gravity. And then this theory then has been tremendously successful in describing the world at large distances, gravity at large distances, solar system, or even beyond that, galaxies, even our expansion of the universe, pulsars, black holes. All this can be described with very simple equations written down by Einstein. So it's a very beautiful, one of the most beautiful theory created by human beings, with a simple equation that we can write on one line. It describes all these phenomena. So this is general theory of relativity. The other is quantum mechanics, which is more subtle perhaps, and in fact much more influential, I would say, which underlines the description of atoms, even elementary particles, photons, lasers, or even this conversation that is happening using semiconductor. All this requires quantum mechanics, and that describes nature at a very, very short distances. And so clearly these two theories have been tremendously successful. One to describe nature at very short distances, one to describe nature at very large distances. And the problem is that if you try to combine the two, you might expect that small quantum corrections to Newton's law of gravity, for example, should be something small. So you have this leading answer is gmm divided by r square, as I said. And there could be small corrections which depend on Planck's constant. This doesn't depend on Planck's constant. And but instead of it being small, it is small because Planck's constant is small. But if you calculate it, it turns out to be infinite. So it is something small multiplying something infinite. So which means that it's not well defined. It is divergent. And that is the fundamental problem. That how can it be that these two very successful and very beautiful theories of nature, when you try to put them in connection with each other, you get absurd answers, namely the quantum corrections to the laws of gravity are divergent, that they are infinite. Divergent meaning infinite. So that would mean that the quantum force between the sun and the earth would be infinite, if this were true. But evidently that's not true, because the classical theory works very well. That means there is something wrong in putting quantum mechanics together with quantum gravity. And this is very well understood. This has to do with non-renormalizability of gravity. It has to do fundamentally with the fact that Newton's constant, the gravitational constant, has dimensions of 1 upon mass square. It is a dimensionful quantity. So the reason for this infinity is also very well understood. But how to deal with it was not understood until recently with the advent of string theory.
So where are we in our understanding right now, and what does string theory come up with to merge these two?
So string theory imagines that the fundamental particles, rather than the fundamental constituent of matter being elementary particles, which are like point-like objects carrying energy, it's an elementary string. So it's like a one-dimensional vibrating fundamental object carrying energy. And this looks like almost a childish idea. You know, what can come out of this? But it turns out to be very deep and very profound, because all the other, you can then look at the string can oscillate in many different ways, like the musical notes of the string. And you can do this Fourier decomposition. I mean, basically, you can look at all the musical tones coming out of the string. Each note corresponds to an elementary particle. And so therefore, you can describe all possible particles by as vibration of the same string. So in this
Hmm.
way, it unifies. This was one of the dreams of Einstein, and
Hmm.
actually Salam partially realized this dream with this Salam Weinberg Glashow theory, unifying the electromagnetic force with the weak nuclear force. That encourages us to find a unifying framework in which gravity and all other forces are unified in the same way. And string theory offers a way to do that. But moreover, because it's like a fluffy uh, object which is vibrating, some of these infinities and which appear in Einstein's theory of general relativity do not appear in string theory.
Hmm.
And Einstein's theory appears to be a kind of a low energy limit of string theory. That also was a very big surprise. That, you know, just
What do you
imagining
mean
that
by
you
low
have
energy limit?
that at low energies, low compared to a very high energy scale. That scale is very, very high. So basically, at normal energies, string theory is indistinguishable from Einstein's general theory of relativity, a part of string theory. But in addition, it has all other particles of nature also incorporated in a very nice way.
Hmm.
So it's a very, very promising idea. But of course, we have not succeeded in finding precisely exactly the same particles that we see, electrons and protons with the same masses. That we have not yet succeeded to do. But that's a very ambitious ask.
Hmm.
But the fact that you're able to incorporate all particles and gravity, and therefore solve this very long-standing problem of unifying general relativity and quantum mechanics all in one shot,
Yeah.
is a very interesting idea. And that's the
Yeah.
reason why many major physicists are working in string theory.
So would you call that the hottest research topic for most physicists these days?
I mean, okay, that's a little bit of a sociological question, you know. So I don't like to get into sociology of science. And I think sometimes it's a bit unfortunate. Sometimes I think string theory is also criticized from this
Hmm.
kind of very sociological point of view, because sometimes fashions in science follow some sociological pattern. You know that some very eminent scientist tells you to do something, or some important advances happen, then it becomes a hot topic.
Hmm.
But I think the right question is it a deep idea? Is it a fruitful idea? Is it a scientifically solid idea?
Hmm.
And there, my answer is very emphatic yes. So whether string theory is also seen ups and downs. You know, sometimes it becomes very hot, and lots of people are working on it. And this is how science progresses. Then you get stuck for a while, and then suddenly new. I mean, general relativity, which is a relatively much simpler cousin, I would say, of string theory. It took 100 years before gravitational waves were discovered. Einstein wrote down these equations 100 years ago. And for a very long time, some people didn't believe in gravitational waves. People said it's ridiculous. Some people ridiculed it. People didn't believe in existence of black holes. I mean, eminent scientists. So
Yeah.
that's the
I mean,
sociology of
Einstein
science. You
himself
know,
wrote a paper on
Einstein
this.
himself wrote a paper showing
Yeah.
that a wrong paper. Actually, it was a wrong paper showing that the singularity cannot occur in nature. And this was
True.
just actually after Chandrasekhar had shown this Chandrasekhar limit, and there was the gravitational collapse was beginning to be understood. Sociology of science is interesting, but I think science is different. Science is about some truth about nature, and string theory has not yet established itself as a truth about nature. This also caveat I would like to state. Some people have therefore tried to say that, okay, until you have a proof, I don't believe in I don't want to think about it. But that's a very short-sighted view, in my opinion,
Hmm.
because many major advances in science happen because, including relativity is an example, that there are some very strong conceptual reasons. Or the Higgs mechanism is an example. It took 50 years to really discover Higgs mechanism experimentally. But
Hmm.
there were very strong theoretical hints. And this is a point that is oftentimes a bit lost on people. Theory, for in a normal language, means something which is kind of very provisional. In physics, theory has a very elevated, prestigious status. Theory really means something, a deep fact about nature. And our understanding of, let's say, quantum field theory. Again, quantum field theory is a framework. Quantum field theory is a bit like string theory. Quantum field theory, there is no quantum field theory of nature. There are models constructed using quantum field theory as a framework, which are theories of nature. The electroweak theory of Weinberg, Salam, and Glashow is an example, or quantum chromodynamics is an example. But quantum field theory provides you a very beautiful, strong, well understood framework which combines quantum mechanics, special theory of relativity, predicts antiparticles. It takes into account locality. So that framework is very powerful. It's so powerful that you cannot really write down some random models very easily. You are very highly constrained by the structure of the theory. The
Hmm.
same was true for general relativity. Once you understand it's a Riemannian geometry and so on and so on, some of these basic aspects were understood. Basically, Einstein had no choice but to write down his equations. Those are the equations. They are more or less uniquely fixed. So this is, in a way, rather mysterious power of our theoretical understanding. And therefore, when some new formalism like string theory comes on the horizon,
Yeah.
which has some deep internal truths, I think theorists like myself feel that it is something that should be taken very seriously.
So when you were choosing your research area, like what were the questions you were asking yourself at that time?
Now, I think clearly unifying general relativity with quantum mechanics is a really an exciting topic for
Yeah.
anybody. I mean, as a broad question.
Yeah.
But of course, when you choose your own research, you usually don't ask such grandiose questions. You start with something small that you can actually deal with as a
Hmm.
graduate student.
Yeah.
So I think you have to, start digging where you can find some little gems, and then if you're lucky, then it connects to something bigger. My work for graduate work, we started thinking about some solitons in string theory. It was
Hmm.
not a hot topic at that time at all. In fact, we were
What
the
is
only,
solitons? Maybe you can explain that for a general audience.
yeah, some kind of a lumpy object where energy is lumped. It's more like a particle, but it's not
Okay.
really like a particle. It behaves like a particle, but it's really like a tangle of the field, the way the
Okay.
fields get tangled. So that's it's called a solitron. And there is some very symmetry between the solitons and the normal particle. It's called the duality. And we were sort of, again, following our nose, we were exploring this. And for first few years, it didn't really receive a lot of attention. But then suddenly it became quite popular. I mean, that's what I'm going back to sociology of science. I think if you follow good, scientifically sound ideas, sometimes you're lucky and it connects to something bigger, and sometimes it doesn't necessarily. But this is how research is done.
So, Atish, you've been involved in calculating the entropy of black holes using Ramanujan's methods. Could you maybe share more details about how you did this intriguing calculation, and how does Ramanujan's approach contribute to maybe our understanding of black hole entropy? Because he had nothing to do with black holes, right? So can you
Yeah.
share more details about that?
Yeah. So I told you about this kind of uneasy marriage between quantum mechanics and general relativity. Uh, and there are some paradoxes. But you can do it in some approximate way. You can try to understand some quantum effects in the presence of a gravity. So one of the consequences of general relativity, as I told you, is the existence of black holes. And A black hole is black because even light cannot escape its gravitational force. The gravitational force is so strong. So as you know, if you to leave the gravitational pull of Earth, you need to send a rocket very fast, which is called the escape velocity,
Escape velocity. Yeah.
right? So the escape velocity is determined by the gravitational force or the size of the Earth. Suppose you made, instead of Earth, you're on the sun, where the gravitational pull is much bigger. Or if you're on some other, if you make the Earth very heavy, many times heavier than it is now, then slowly the escape velocity also will start becoming larger and larger. And once it reaches the speed of light, then, as I told you, in general relativity, this absolute speed limit is respected.
Yeah.
So nothing can travel faster than the speed of light. So therefore, nothing can escape the
Yeah.
gravitational pull of this object. And that
Yeah.
object is called a black hole.
Yeah, but can I
And
ask a distractful question just here? Sorry. So, but then how did if nothing can escape out of the black hole, then how did Hawking come up with those radiations which come out of the black hole?
this is the classical picture, because this is if you ignore quantum effects altogether.
Okay.
And Hawking then had this idea that, okay, we don't know how to really combine quantum mechanics with general relativity. So that we will not try to do. But let's try to do a simpler problem, namely treat gravity in a classical way, but consider in its background other fields. So take a black hole and consider other fields like electromagnetic field or electron, and treat those particles quantum mechanically. So it's called a semi-classical approximation, that you treat gravity classically, but you treat all other. This is strictly not. In some approximation, this is valid,
Hmm.
but in a quantum mechanics, actually, this is a very important result of Heisenberg. That in quantum mechanics, it requires that either you have everything quantum or nothing quantum. You cannot have some objects behaving classically and some objects behaving classically, quantum mechanically, because of Heisenberg uncertainty principle. He had some very nice thought experiments to show that.
Yeah. Yeah.
So Hawking said, okay, but in a certain approximation, you can do that. If in that approximation, you take a very big black hole and you imagine some particle moving in the background of this black hole. But as you know, in relativity, every particle has an antiparticle. And in
Yeah.
fact, as we speak, even in this room, constantly a particle and antiparticle pair is created and it is annihilated
Hmm.
everywhere, all around us. We don't even notice it because it lives for an extremely short time, in picoseconds or even attoseconds. So we don't notice it. But now, if this happens near a black hole, so the black hole has the surface which is called the event horizon of the black hole. So if once you cross that horizon, the gravity is so strong that you cannot escape. But now, just a little bit outside of the event horizon, it can happen that these pairs are being created all the time, and one of the pairs can fall inside, and the other pair then. Normally, if it is happening in this room, the particle and its partner, they can always meet each other and annihilate. They so you don't notice anything.
Yeah.
But what Hawking showed was that actually once in a while, one partner can fall inside, and the other partner then has nobody to talk to and nobody to combine back with.
Hmm.
So that partner is kind of again single and ready to have fun, and then it goes to. Yeah, so it's kind of a married couple, and then the one partner falls inside, and the other partner is single now. And that single particle will show up to a far away observer
Hmm.
as though it is coming from the black hole.
Okay.
And Hawking, of course, showed something very beautiful. Bekenstein, actually, and Unruh, many physicists have contributed to this. This is known as Hawking radiation. That, in fact, what is coming out, it looks exactly thermal. In that,
Hmm.
it looks like black hole is really not black. If you take this semi-classical effect into account, black
Okay.
hole is really like a hot piece of metal or a hot coal, and very low temperature radiation is constantly coming out of it. It's like heat being radiated from this object, and that raises the question: if the heat is constantly being emitted from that object, We understand the heat of a coal, a piece of coal or a piece of metal is hot because the little atoms inside in the metal are vibrating. And if the temperature is high, then the atoms are vibrating faster. If the temperature is low, then they are vibrating slowly. So this is called the kinetic theory of, this is basically explaining or statistical mechanics, which is known as statistical mechanics, which is basically an atomistic explanation of heat and temperature and thermodynamics. That basically heat is nothing but motion, meaning we feel that the room is hot because all the atoms in this room are moving very rapidly around us. And the average energy of these atoms is related to the temperature in the room. So if you increase the temperature, if you put a heater, the average energy of atoms goes up. And so when it is very hot, it means that all the atoms, oxygen and nitrogen in this room are moving very fast. So basically you explain heat in terms of motion. So it reduces thermodynamics to basically mechanics.
Yeah.
It's called statistical mechanics. It's kind of statistical. And then the question arises, what is the mechanics that will explain the temperature of the black hole? Or there is another quantity called the entropy, which is related to the second law of thermodynamics, which is a more fundamental quantity than temperature. And Boltzmann understood that in the context of normal matter.
Yeah.
And what is nice about this, basically it's defined in a simple way that if you put a heater in this room, at room temperature, and you calculate how much heat is being given to this room, basically the entropy is proportional to that heat that is being added, and you divide it by the temperature. So change in entropy is the amount of heat that you're adding to this room divided by the temperature, which is 300 degree Kelvin. At the room temperature is 300 degree Kelvin. So that is what explains the entropy. So the entropy now, that's called the entropy, that defines the entropy. And what Boltzmann showed was that entropy is a kind of a window into the microscopic structure of the atoms in this room. So you cannot see the atoms in this room. When you put a heater, calculate the heat added, divide by the temperature. That is equal to the logarithm of the number of ways the atoms can move in this room. Let's take a simpler problem. If I give you a box and there are n small boxes inside a room. Now, suppose you divide this room up into small boxes. Then it becomes a counting problem, right? Suppose I have n boxes in this room, and let's say suppose I have r particles, r number of particles. Then it becomes how many ways I can put r balls in all these so many boxes.
Yeah. We can do
It's a
permutation combination.
problem, right? Some n factorial, right? It's a counting problem. You take the logarithm of that. And surprise of surprise, that logarithm is precisely the entropy that you can calculate by putting a heater. And of course, for that, you have to give the size of the box. That is basically given by the thermal wavelength of the atoms. So if you do this very simple counting problem, you can explain the entropy of this gas in the room, entropy of air in this room. And that was one of the great successes of kinetic theory of gases. Going back to Maxwell, Boltzmann, Gibbs, all these people. And it was even much lot before quantum mechanics, almost 60 years before quantum mechanics. They were really ahead of their time before any real evidence in fact, it is many people, chemists had understood, but many physicists actually very strongly opposed the idea of atoms. Like I think Ernst Mach was very dead against it, to the extent that Boltzmann, it probably, part of the reason which probably caused him depression was that he was not accepted. This idea was not accepted by some of the leading physicists of the time or philosophers. But eventually, we understand this as one of the most profound and important contributions to physics, that entropy is the logarithm of the number of states, microstates of the system. Now the question arises, how do you explain if the black hole has temperature, like this air in this room has temperature and it has entropy, like air in this room.
Yeah. Then what is it made up of?
What is
Yeah.
it made of?
Yeah.
It's a very important, very beautiful question. And string theory offers an explanation, a very beautiful explanation for it, for a somewhat idealized situation of supersymmetric black holes. So these are black holes with some higher degree of symmetry so that you can do the calculations exactly. So it's not a black hole that you see in the sky. That problem is much harder. But Boltzmann principle is very general, you see. So therefore, Boltzmann says that give me any physical system, which in a thermal system, if it has temperature and entropy, no matter what system it should always be the case that the atoms of that system, they can arrange themselves in billions of different ways. And you calculate that number and you take the logarithm, that should agree precisely with the entropy of that system. And so it can be an idealized system. It can be a system which is not there out in the sky. If that system exists as part of it, if it is possible in your theory, and if your theory is not able to explain it, then your theory is wrong. So this became actually a very extremely stringent test of string theory. That is, string theory, we are still not able to find direct experimental evidence. But this becomes a very interesting question, that there are black holes within string theory. Since string theory contains general relativity, it contains quantum mechanics, and therefore these black holes have entropy. And if you are not able to explain the entropy of these black holes internally within string theory, because string theory claims to be the theory of all particles, so there is nothing you can add to string theory to explain.
Yeah.
And this you are able to explain. In a very large number of black holes, you can actually do this counting very precisely. And this leads to this beautiful connection with Ramanujan's work, because Ramanujan was interested in, he was combinatorics. He had one of the very important problem in combinatorics was the following. How do you partition an integer? Okay, so you take an integer like 3. You can write it as 3, or you can write it as 2 plus 1, or you can write it as 1 plus 1 plus 1. So there are 3 ways to partition an integer like 3. So that's called, the P of 3 is 3. Okay, P is the number of partitions. Take 5 now. You will see that the number of partitions of 5 is much larger. It can be 3 plus 2, it can be 1 plus 1 plus 3, it can be 1 plus 2 plus 2, and so on.
Yeah.
And now you can ask, what is P of 100? In fact, if you've seen this movie of Ramanujan,
Yeah. The
there's
man
a
who
very
knew
good scene
infinity.
there, the man who knew infinity.
Yeah.
This was one of the problems. Suppose you want to calculate P of 100. It's an impossibly difficult problem because it grows exponentially, the number of ways you can do this. But Ramanujan, being Ramanujan, he related to something called modular forms. He discovered that this problem can be related to some very symmetric, beautiful functions in mathematics, which are called modular forms. And modular forms are, like, you are familiar with functions like x or x square, x cube. These are functions, right? Functions of x.
Yeah.
You plot, you have x and you plot the function. So if the function is x, then it's a linear. If it is x
Yeah.
squared, then you can draw any arbitrary curve. That's a function.
Yeah.
But this generic function is not very symmetric. But if you take a function like sine of x, then it is periodic. It's a very nice function.
Yeah.
If you take x square, it has a very nice symmetry. It is symmetrical. X going to minus x, you get the same answer. Right? So functions can be symmetric. And modular functions are a particularly nice class of functions which are symmetric under an infinite group, some infinite number of transformations. So sine function is just periodic, meaning if you translate yourself by 2 pi, you come back to the same function. You keep translating, you come back to the same function. X square is symmetric under reflection. X going to -6, it is symmetric.
So can you give an example of a function which is periodic but not modular?
Sin x is a function which is
Okay.
not modular.
Okay.
It's periodic, but it's not modular, because modular means it's not
If
only
you apply
periodic, but it
transformation,
has
it's
some
yes.
additional symmetries.
Yeah.
It has
Okay.
much bigger symmetry, much more
Okay.
symmetric. And because these functions are so symmetrical, it's a bit like you can draw any figure, but a circle is a very beautiful object. Circle is you can draw hexagon. So hexagon has a symmetry. If you rotate through 30 degrees, it comes back to itself.
Yeah.
If you take a square, it is a figure. But the most beautiful symmetric figure is a circle. You can keep on rotating it even by small angle, and it comes back to itself. So these functions, modular functions, are a bit like a circle. They are they're symmetrical under a big symmetry transformations, very big symmetry transformations. And because of that, you can derive some nice properties of these functions. And from those functions, you can figure out, it's hard to explain how, you can figure out the number of partitions of this integer. So basically, this counting problem, which Boltzmann was interested in, gets related to a counting problem that Ramanujan was interested in. So basically, there is this rather amazing connection through black holes between Hawking, who discovered the entropy, and then Boltzmann, who said that entropy should be related to logarithm of some counting. And Ramanujan, who figured out how to do that counting in some interesting way using some modular functions. And that's where the work of Ramanujan becomes important.
Okay. What sort of contributions were you able to make?
So people were Strominger and Wafa and Ashok Sen and some other people had understood the kind of the first term in an infinite expansion. So basically, if you take a logarithm of a large integer, that's supposed to be because number of ways is an integer, right? So you take the logarithm of a large integer, you get the entropy. But the entropy is not doesn't have any integral properties. If you look at entropy is like heat added. You're putting a heater. There is no integer there. But what we showed was that there are actually small corrections to that entropy. If you add up those entropies and take the exponential, you actually get an integer. So our contribution was to really compute the quantum entropy of black holes, meaning not just the first leading piece, which Boltzmann was interested in, but also including the fact that the black hole has finite size, the finite size effects of the black hole. All the order to all orders. It's actually highly non-trivial to do this calculation. And very surprisingly, that calculation agrees with another very highly non-trivial calculation where you do the counting using Ramanujan's methods. And the two precisely agree and you give you exactly the same integer, like 512. So 512 comes out of some counting problem, and 512 comes out of some geometric properties of a black hole. And the black hole is a very geometric object. There is no notion of an integer there. It's some very beautiful connection with integrality. It's sort of seeing the quantum structure of the black hole space-time through this indirect method. I think that's why I believe that this result is important.
So Atish, you are currently the director of the Abdus Salam International Center for Theoretical Physics. So could you shed some light on how ICTP contributes to the advancement of physics and what sort of impact it has on the world today? And how do you facilitate progress in this field?
So you told me that you are from Karachi, right? From Pakistan?
Yeah.
So from Abdus, founded by Abdus Salam, who got the Nobel Prize for some of this important breakthrough unifying two of the forces of nature, namely electromagnetic force with weak nuclear force. Yeah. So in some sense, this work in string theory is a kind of it was one of the milestones in this search that has been going on for the last 100 years. But Salam had another very kind of a driving thing. So in this way, scientifically, I feel quite close to Salam. But also, he had this humanitarian aspect to his personality and also to his kind of his life goal, I would say, that he felt that science really should be globally available. And he wanted to go back to Pakistan and he had to leave the country. So he wanted to basically create a place which will be an international hub for science, where scientists from all over the world can come together. And so, and really combining excellence with inclusion, meaning really making really top of the best science, the frontier science available to anybody sitting anywhere in the world. And that is the fundamental mission of ICTP. And through science, promote international cooperation. So therefore, this mission was also very close to my heart. It was really important for me to be able to give back to society in this way, that not only do we do your own physics research, which I'm of course very happy to do, but also contribute in some way to build the scientific communities. And ICTP plays a very, very important role. So just to give you an idea of the scale of ICTP, we have about 6,000 scientists who come from all over the world to the campus in Trieste. ICTP work done at ICTP has contributed to many major breakthroughs, including a number of Nobel Prizes and so on. So it's not, it's the quality is very high, but it is open to the whole world. And 2/3 of the scientists come from developing countries, and they are fully funded by ICTP.
And is it just theoretical physics?
No, and now we are expanded and we do mathematics, condensed matter physics, quantum information, quantum computing, climate modeling, artificial intelligence, quantitative life sciences. So it's now the name is there. I mean, because it has become a brand, so it's difficult to change it.
But it is a living, dynamic institution on its own.
Yeah. It's a living, dynamic institution, which is really International Center for Theoretical Sciences, I would say. It's a little bit like CERN. CERN was started as it's called Centre Européen de Recherche Nucléaire. That's CERN, which means nuclear research. But it's no longer doing nuclear physics, because nuclear physics, the frontier moved to particle physics and even very high energy particle physics. So, but the name remains. CERN is still called CERN. It's the same way.
Yeah. As we started this conversation, the fashions have changed.
Yeah, that's right. I mean, the science frontier has changed, actually.
The science frontiers have changed.